Hello, welcome to the section 3.7. We will give you some brief introduction to this section today. The title of the section is Modeling Uncertainty, Fuzzy Situation, and Grey Methodology. This section will focus mainly on uncertainty modeling, including, for example, fuzzy set, gray systems, and rough set and their applications. The organizer of this section. The first one is Professor Sifeng Liu from Institute for Gray System Studies in Nanjing University of Aeronautics and Astronautics in China. And then is Professor Yingjie Yang from Institute of Artificial Intelligence at Montpellier University in the UK. And Professor Alexander Ryjov from Russian Academy of Science. This section have 13 papers accepted and will be presented in the conference. Here you can see this list, including authors from several different countries. You can see we have 13 papers cover a very wide topic, and it involves different uncertainty models. For example, gray models, fuzzy models, rough models, and their different applications in a wide range of topics. Because we have so many papers, so within the very limited time, I would not be able to talk about them one by one. As an example, I would give a little bit detailed introduction to the first one. The title is A New Way of Thinking to Solve the Decision Dilemma of a Rule of Maximum Value. Here is this. We would cover a number of topics for this paper. For example, the first, we talk about decision dilemma of a rule of maximum value. And then we talk about the weight vector group of kernel clustering. And then we talk about several functional weight vector groups of kernel clustering. And number 4, we talk about the weight coefficient vector of kernel clustering for decision making. And then in the end, we talk about problems to be further studied. Now we discuss the first one, the decision dilemma of rule of maximum value. The rule of maximum subject expected utility. This rule mainly coming from this two following literature. For example, the first one, the source and methodology of statistical decision, comes based in 1763. The second one is Bayes' decision theory and the principle of maximum subjective expected utility, written by Savage in 1945, the foundation of statistics. The basic principle to solve a decision problem is like this. Rule of maximum subjective expected utility and rule of maximum expected value for objective of benefit type, rule of minimum expected value for the objective of cost type. So you can find more details from the literature we just covered about this. In gray clustering evaluation decision, people usually determine the expression of decision object according to the rule of maximum value we just discussed about. Here, assume that we have sigma I is a gray clustering coefficient vector. So, for example, here you see you have sigma I1, 2, 3 for S. And I itself is a number represent the different components. When the value of the components close to each other, it's difficult to determine the expression of the decision object I. So here, the task is to select which is the best decision. But if they are very close to each other, it's difficult to differentiate them. The smaller the difference, the more uncertainty the conclusion would be. The first situation, all the values of the component of a Grey clustering coefficient are equal. So if they are all equal, then you cannot separate one from another. The second situation, it's difficult to differentiate the maximum component from other components. So that means they are close enough. And it's very hard to get a certain conclusion. Another situation is that the conclusion by the rule of maximum value collide with the conclusion by considering the value of all the components in an integrated manner. I mean, if you just look at the values according to the maximum rule of maximum value, then what you selected is different from if you consider everything together. Here I show you an example. For example, we have 4 classes: excellent, good, medium, and poor. And here we have some decision components like this. So you have 0.18, 0.35, 0.36, 0.11. And if you choose the maximum one, certainly that's 0.36. So in that case, we conclude that it should be medium. But if we consider everything together, obviously this is not reasonable. So here we have the decision dilemma. How to solve this problem? So this problem happened because of that the people pay attention to maximum value only. When you pay attention to one value only, then you overlook the impact of the others. So that's the problem. Then what would be the solution? The basic idea is to solve the problem by considering both sides of the component K. So that means we consider all other components together. This should be able to avoid this problem. Then we propose the weight vector growth of kernel cluster. So this is the definition, right? So here, because of time, I do not go into depth, but you can see that we define a number of parameters: need 1, need 2, need 3, and you have need k and need s as well. So the need k is called a weight vector group of kernel clustering. And here the subscript actually can turn out to be 1 to k minus 1 k, k plus 1 to s. So that's the need k. Then ws in the equation is the maximum component of the vector. The kth component ws can be taken as a center, and the other components in both sides could be considered together. The third, we talk about several functional weight vector growth of kernel clustering. Again, we have this proposition about need, and need k is a weight vector growth of kernel clustering. So suppose that s equals to 5, then we can compute the need. We got these values. Then k, according to the k equal to 1, 2, 3, 4, 5, is Here the K is the weight vector group of kernel clustering. Suppose that S is 10, then we can let need 1, need 2, need 3, we can calculate all these need K. Then need K is the weight vector group of kernel clustering. The number 4, we talk about the weight coefficient vector of kernel clustering for decision making. Here, R2 is the weight vector group of kernel clustering, and the outcome would be the weighted coefficient vector of kernel clustering for decision making. Here, we have another definition. Assume there are n decision objects as different Grey class, then we have omega ik to need k times delta it. So this omega need ik is called the weight, the coefficient of kernel clustering for decision making of object I about Grey class K. And omega I it composed of omega I1, 2, 3, and omega S. This sequence of omega put them together called the weighted coefficient vector of kernel clustering for decision making of object I. So here we show you another example. Again, we consider the 4 class: excellent, good, medium, and poor. We take S equal to 4, we calculate delta I, then we get the paradox. And then we can calculate the need. From the omega equation, we have all omega calculated. From this, if we select the maximum omega, we got omega I2, 0.27. That is the maximum one. So obviously, our conclusion come to that it should be the second one. Good. So this solves the problem we have already raised. Right. What to be further studied? The problem to be further studied include the properties and the characteristics of the weight vector group of kernel clustering, new weight vector group of kernel clustering for practical applications, and the suitable conditions of different weight vector group of kernel clustering. So that's the problems that need to be further investigated. That's the contents of the first paper. Here, limited by the time, I could not go to other papers, but this have already shown you that the contents of this section, and it covers different uncertainty models, including green models, fuzzy models, rough models, and their application in real-world practice. So uncertainty is a big problem in modern society. The solution to this problem will have significant impact on our modern society development. So hopefully you would be interested to this content of this section and join us in the coming conference next year. All right. Thank you for your attention.